And I had a debate whether I should wear my Einstein tie, or which I bought last year because it was the 100th anniversary of general relativity. This year happens to be the 100th anniversary of the prediction that there would be gravity waves, although it was a sloppy prediction. And if you want to read more, once you hear my talk, you actually want to read more and understand some stuff. Two colleagues from Mexico and I wrote a brief history of gravitational waves, and we talk a lot about what went on. And the whole history of gravity waves was mostly full of missteps, right? This great success that we're celebrating here at 100 years after the original, having the equations of general relativity in November of 1915, and then early 1916, the prediction that there'd be gravity waves. There was a lot of controversy, and you can read about that. And Einstein even went to write a paper with Rosen claiming there were no gravity waves, and they sent it to the Physical Review, which sent it out for review, and that made Einstein very upset because the reviewer, who happened to be Robertson, who the mathematicians know was a very good mathematician, very good general relativist, pointed out there was a mistake in it and sent it back to Einstein, and Einstein got so upset he withdrew the paper from publication and resubmitted it to the Ben Franklin, where they offered to eventually publish it. But by the meantime, his new postdoc, because Rosen had gone into another job, convinced him, ran into Robertson, was convinced that the calculations were wrong and how to redo them properly, and they do that. So there was sort of nearly 40 years of missteps on the theory of gravity waves before finally people realized that there were these mathematical gravity waves, and that Einstein was convinced that maybe there were gravity waves. Rosen was never convinced that there were real gravity waves. And then another few years, more than a decade, before people came to agree that they might actually carry energy. At that point, people started to do that. So if you're interested, we put a lot more of those details in this paper, and I would spend more time talking about that. But I want to talk about the actual measurements and the discovery and some of the things it might mean, and leave some time for discussion. So that's a tricky thing. Let's see if I can do this remotely otherwise. Okay, so February 11th, there was an announcement, a general press conference announcement. This is a picture of the executive director, David Rice, and he got up and he was really excited, and he said, "Ladies and gentlemen, we have detected gravitational waves." And he couldn't resist saying, "We did it," because if you look, they were working on detection of gravity waves for 60 years, and LIGO itself has been around for almost 40 years, the pieces that went into LIGO. So this is a long story with a lot of mistakes, and yet somehow managed to convince people to put a lot of money and a lot of time and a lot of effort into it and get this done. And so that's a picture of him being excited. Here's the data as seen by the detector, the LIGO detector, which is in Hanford, Washington. So this big red L up there, and then the blue L facing the other direction is the Livingston detector, which is in Louisiana. And the distance between the two is 3,002 kilometers. And that turns out to be 10 milliseconds of light travel time. Right? And so the two signals, you can see the signal and you can see the predicted signal that is fitting a template to it of two merging black holes and the two. And you can see the Hanford data shifted by 7 milliseconds and flipped over, superimposed, so you can see what the waveforms look like. And so they were all excited about this. And they made this announcement. Now, in fact, they were even more excited because they actually saw this on September 14th, and a little bit leaked out of the LIGO community to some of us who were paying attention, and then they clamped down. Right? But we heard they made this detection and so forth. And as Tony was saying, when Advanced LIGO turned on, they detected this very quickly. And very quickly, they were actually in the engineering run from being turned on. So LIGO had been built, it had run for almost 5 years, been shut off for 5 years for upgrades, and they turned it on and they're doing engineering tests to make sure everything is working. And they've done a whole series of tests, and They were planning to do a couple more tests, but they were so far behind schedule, they decided to go home because it was 1 o'clock in the morning in Louisiana. And they went home, and a postdoc who was sitting at his desk in Germany saw this data come across, and this signal came, and this email came out, and they saw this event. And they go, what is this? What is this? Well, typically they inject false events every now and then so you can see it, but this was during the engineering run. And so half the people are thinking this can't be a false event because the 5 guys that are allowed to put these false events in, they weren't even on shift, they weren't, it didn't make sense, right? And so most of the people on the team thought right away, this is a real event. By the end of the day, by 24 hours from getting these emails and asking everybody, that's why it was leaking out, and then the spokespeople clamped down. So you didn't hear anything. There was not an official announcement till then, but a lot of people were excited. A lot of stuff was going on. So my colleagues and I did some stuff like teaching a course on gravity and some other things because we knew things were coming. But that's how excited we were after 100 years, right? If you wait some long enough time, it's that way. Okay, so here are the 2 black holes, those black things, and they're going around, and that green stuff is the ripples in space-time caused by the gravitational effects of those 2 black holes. And you see they orbit around each other. They're sending out energy in the form of gravity waves. That was a critical aspect. Do gravity waves carry energy or not? And the answer is they do. You get this pulse going out, and it's sort of rippling across space. So you're getting to see it going on, and we're going to come and see it go by the Earth. And as you see, the Earth will start to shrink and expand a little in the 2 different directions. Now, this scale is greatly exaggerated. Right? The size that something that's 4 kilometers long changes by is by 1,000th the diameter of a proton. So it's a really tiny effect, but in order for you to see that, this would just to see what's going on. Okay, so this is a gravitational wave event, 2015, September 14th, right? They don't happen that often, so you can just give them a date. Produces a strain that is a change in the distance between 2 objects, which is 10 to the minus 21 of the distance between them. So 4 kilometers times 10 to the minus 21 gives you 1,000th the size of a proton. It's really quite a small effect. How do they measure that? Well, it's really tough, okay? So when you do the fit to that template, you say there are 2 black holes that are orbiting each other. One has a mass of 36 times the mass of the sun. The other one has a mass is 20 times. So roughly 2 30 solar mass black holes orbiting around each other. And they merge together to produce a 62 solar mass black hole. And they send out 3 solar masses times c squared of energy in gravity waves. And that's hard to detect, right? Now, I'll point out to you in a couple of slides later, that's more energy that is coming from all the stars in the visible universe. So we're arguing about is there 100 billion galaxies with each having 100 billion stars in them or 20 times that much. It's still, it's still a lot of energy and it's still tough to detect. This event took place long ago. It took place 1.3 billion years ago. It has a redshift of about 0.1, right? So the universe was 1.1 times smaller than this now. The universe is expanding. And it didn't get to the Earth until September, right? So that's the exciting part, right? That you're beginning to see stuff that stretches across the universe. And this is the first event. And this is what in the old days we used to call the typical event, right? It's beautiful, right? You search through your data and you find the one that looks so great. You publish that in your paper. You couldn't have asked for a better one. And this came 2 hours after they left from doing the experiment where they were going to run trucks, run a truck over a big bump and see if it could affect things. Okay, so what are the stages of the event? Well, you have 2 black holes and they're orbiting around each other. Well, normally we have like the Earth orbiting around the sun. It's pretty stable. It's been that way for 4.5 billion years, right? It's not losing that much energy. It's staying in that nice orbit. But 2 big black holes are in close orbit around each other, radiate a significant amount of power in gravity waves, and that means they're losing energy. They're getting closer together. So the first part's the end spiral. So they're orbiting around this sort of nice orbiting like we're doing around the sun, but it gets faster and faster until you get to the point where the 2 black holes just touch their event horizons. And then you have a merger and then a ring down, and you'll see these, I'll show you so forth. So it's in-spiraling, it's touching, it's becoming one black hole. Right? Those are the stages that we're looking at. Okay? So this a slide in honor of Brexit. You can see the scale of the black holes over on the right-hand side. You can see the scale of the black holes. You can see England plus Ireland. You know, unfortunately, you can't just take part of England and take it out of the EU. You're going to suck everything down in a situation like this. Okay, so the other thing that goes on in this thing is you do calculations of numerical relativity. What that means is you have these complicated equations of general relativity, which should look simple and look beautiful, but are difficult because it's basically a whole bunch of nonlinear equations you stick together. And so you solve them by put them into a computer, and you have code that does the calculations carefully. And you do a whole array. You try all different sizes of masses and different orbits and so forth until you find the one that most closely represents the event. Okay? So you can fit to this. If you measure the frequency, that tells you the masses. That tells you how bright it should be. You can figure out how far away it is. So it's a standard candle. You can predict how big the strain should be, and you measure the strain, and you see how far away it is. So you can get the source distance. You can fit to the masses. So the best fit is 36 plus or minus about 4 solar masses. You can fit to the other one. It's 29 plus or minus about 4. And you can see the end product is 62 plus or minus about 4. And you can see that you get about 3 plus or minus a half, right? Solar masses of energy in gravity waves, using E equals mc squared. So that's a lot. So this is 50 times brighter than all the stars in the observable universe at the present time. Just measure how much light's coming in. That total amount of energy is less than this by a substantial amount. So this is one of the most kind of powerful events. The other kind of events that are close to this are gamma ray bursts. Everything else is much less powerful in terms of what's going on. Now there's another thing that you should notice. Here's a plot of time, right? So this is measured in fractions of a second, a third of a, we're coming to a third of a second, right? Half a second, almost half a second. And as the black holes start moving together, the velocity picks up. And you will notice out here, it's going better than half the speed of light. So imagine this, you've got two objects in orbit around each other, and they're moving near half the speed of light. It turns out you need a very high speed, you need big quadrupole moments to produce gravity waves. This is almost the ideal situation. For the rest of it, this is how the separation looks this time. So you can see the frequency and the chirp up. Okay, so here's what it sounds like if you use the thing we use for birds. So that's shifted, that's the real sound, and this is shifted into the audio so you can hear it. So you're plotting the time, and you're plotting here the frequency. So this is just, so in the paper I got an example of a chirping sparrow. The chirping sparrow has a rising pitch. The pitch-patrol bat has a falling pitch. So I leave it as a problem to the physics students or the engineers. Why, if you're trying to echolocate things, do you use a falling pitch instead of a rising pitch? So why do sparrows go one way, why do they go? So it's interesting that you can do this, and this is technique that they already developed. They were looking for sort of structures that look like this, and they were looking for sounds that look like that. Because one of the things that I had been teaching in my courses for years and so forth, people expected to see neutron star mergers, and they would be very nice high-pitched things. But black holes, we didn't know how many existed. So this is just a beautiful graphic showing the two black holes and this nice star cluster behind it, and you can see how it distorts the light that's coming from the various stars. So the stars aren't really moving around, they just appear to move around because space is being bent and light is traveling around it. And you'll see they orbit around each other and they orbit around each other, and they get slightly distorted, and then they touch, and it gets round right away. The ring down is very fast. Right? The black hole merges, you would think it'd be looking like a dumbbell or, double cherry or something like that. It just rings down into a sphere very quickly. Okay, so let me go back a little bit in history, the early attempts to gravity waves, and I'm going to do it slightly out of order. I'm going to tell you the one that gave people encouragement, because the field fell into despair based on the early attempts and the failure of the early attempts. But the thing that happened was that we got some indirect proofs that gravity waves existed. Okay? So Hulse-Taylor discovered this binary pulsar, which is, we believe, two neutron stars orbiting each other. We have samples of those, so we have some idea of statistics of those. And they measured the orbital period. They have two beautiful clocks that are orbiting around each other. You can see the pulses coming from them, measure the orbital parameters extremely precisely, and you can measure various things. And so these two things are orbiting around each other, and they've been moving along, and they're radiating away. So the interesting thing is the orbital period is just over 8 hours for these two things who are as massive as the sun. They're orbiting around each other in 8 hours. That's not impossibly fast. But the rate at which they're orbiting changes by 76 milliseconds per year, and you watch that as a function of time from 1975, when it was discovered, out 2005, what's in this plot. And you can see the data points, and you can see the prediction of what the change in the orbital period should be, cumulative change should be over that time period. And you can see it fits extremely well. And you will notice they were given the Nobel Prize in 1993. So I told the committee they have to be careful about that. You notice there's a gap in the data. And the Nobel Prize disrupts your activities. Fortunately, after a while, things settled down. They went back, fill that data points in, and now there's data up almost to the present. Right? So these are two neutron stars that are going around each other. You've got these, you've got some others for samples. You can make a prediction that LIGO, advanced LIGO, should be detecting at least a few per year, on the scale of 3 per year of these. That was why we were able to convince NSF and the Congress. There was something we could calculate and say that was going to happen. So this is the thing that reinvigorated the field when this got taken in this time period. Because what had happened before was a series of things. You can hear a bunch of details, but this young man, who was a very good engineer, but very interested in aspects and so forth, his name Joseph Weber, and he thought he should get in the gravity wave detection business, and he actually thought, well, there's a couple kinds of detectors. He thought about using lasers, because lasers were a new thing in those days, but he also decided to make a resonant bar. And so he decided to make what's now called a Weber bar, a resonant frequency, and started building in the 1960s. It took him a number of years, and he started claiming detections. And the detection level was very high compared to what anybody would say. So here's a picture of Joe Weber and the resonant bar. He had two of them, one in Maryland, one at Argonne National Lab. And it's just this big piece of high quality aluminum made to resonate very well, and then a set of detectors to measure the resonance, right? And so if you're physics majors, you'll know a standing wave is going to have the biggest stuff in the middle, so that's what you'll do. And so Professor Yang gave me this beautiful picture. I assume it's okay, it's legally okay to say this, but I assume it's not too racy. But he was claiming he has detections. She's saying no, right? And so forth. But this had a resonant frequency of 1660. That I believe is 1660, right? And what you're doing is you're needing some gravity waves with this frequency to come through and excite your bar, right? So if you're an opera singer, you can do it. You can move your voice to get through the resonance of the glass and break the glass, right? But that's the, Here, he's looking at a very narrow frequency range. He was claiming to see significant signals coming from the galaxy. That was disputed by theorists. It wasn't disputed by observers. They came and looked at his data. They couldn't figure it out. People started building their own bars. And the first generation of bars, nobody else saw what he was claiming, right? And then they started building cryogenic bars during this time period. And people were beginning to be discouraged by this idea. And Hulse-Taylor pioneer came along. And that excited people to think about other stuff. But at that time, also, I pointed out, he also gave the first public lectures on laser physics, right, and how lasers worked and so forth. He did a lot of stuff, and actually the American Astronomical Society gives a prize out for people, the Weber Prize, for people who build best astronomical instrumentations. So we give them a lot of credit. So now when I'm jumping on to the 40 years of LIGO, okay? And so Tony says you knew part of the group, but this is the first one I met. I met when I was a student at MIT. I went down to Ray Weiss's lab, and he was sitting on the floor with his corncob pipe and soldering. So that was my first introduction. And so what happens is Ray Weiss comes up with a report in the good old days when you just wrote a short report to what's going on. But it turns out the idea of a laser interferometry gravity detectors was first outlined by two Russians in '62 and tried to be revised by Vladimir Brzezinski. But things were not so good in the USSR in those days for what was going on. So Ray Weiss had this idea and started working on it, and he eventually convinced Kip Thorne that's important. Here's the progress report. That's the first diagram of a laser interferometer, right? This is the kind of thing. So he was getting money from the Air Force at that time, and you just wrote a report back to the Air Force and what you'd done and what ideas you had, and you put it in there. And the Mansfield Amendment got passed that year, which said you could no longer, as Senator Mansfield, you could no longer use military funds for anything that wasn't for defense, and so he had to go to NSF. Right? That's why Tony got in the loop. And so what happened was, even more than that, Steve Weinberg had been at MIT at this time and was teaching the course on general relativity and gravitation, which turned into his book. But then he left to go to Harvard, and so the chair of the department got Ray to give to teach the talk. And so he had trouble explaining what Weber was doing, and so he ended up having special seminars and discussions with students, and they came up with the idea of using the gravity wave interferometer. So sometimes it's useful to teach a course and have interactions with students. Often it is, actually, but we don't want the students to know that too much. And so here are the people that ended up doing this. So Kip Thorne is a theorist, most famous for his work on a movie recently, to release what was going on. So Kip Thorne got excited by Ray Weiss about this idea and wanted to hire Brzezinski, but the Soviets wouldn't let Brzezinski out of Russia, out of Moscow at the time. And so Ray suggested that Ron Drever would be a good thing because he'd done the Drever-Hughes experiment and had a tremendous reputation as an experimentalist. Well, that turned out to be the beginning of a hard fight. Those two personalities didn't work very long for a long time. And eventually they put someone named Roby Vogt in charge of it. That was a three-way fight. And then finally Barry Barish became the head of it. And that worked because he knew how to manage things. And he had the vision that we should start building LIGO in pieces. You build it and build it in the structure that's going to be good enough and just keep upgrading it. That's why he had the idea to make advanced LIGO all along in his back pocket. And so that's what he knows. So these are the three gentlemen that really started things in a big way. And Ray Weiss, because Drever went there and was so good, Ray Weiss had to put in a bigger proposal, which became eventually the LIGO proposal, but also a proposal in NSF, which got sent to Germany to be reviewed. And that started the European one because they said, hey, this is so much better than the bars. That's it. So that's how GEO 100 and Virgo eventually got going. Okay, so in 1979, so that's roughly 40 years ago, I do the math, the MIT got a little bit of money and then to develop the idea for the whole thing. And they put a proposal in '83. And the first draft that I heard and saw was they were talking about 30 million, but when the report actually got done at the end of the year, it was 100 million. By the time it got done, it was 252 million for LIGO, and then advanced LIGO, like is another one. So it's going towards $600 million just in the NSF cost. And so advanced LIGO finally got operating in 2015, and within hours of being left alone, it started seeing that, it got lucky and saw the typical event. So here are pictures of the two detectors. There are 4-kilometer long arms with a central housing area and a place where people are doing experiments and so forth. And my colleagues and I made a mistake. This was miles, and we wrote kilometers. The real distance is 3 kilometers. So that's I have to apologize for that in the article, or we have to fix it eventually.
A laser beam is split
so here's how it works.
Sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base.
Plus.
The light waves come back lined up in such a way that they cancel each other out.
So they're half a wavelength.
You add them together, you get nothing.
This
you
is
get
ray.
a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
That reminds me of a 1950s film. So it doesn't have to be exactly the same length. Just be close, and you want it half a wavelength off, round trip, so that it's canceling, right? Because you look for a change from canceling. That's it. So I'll show you another movie, because the reality is a lot more complicated. This is what LIGO really looks like. There is a laser, which is operating at roughly 100 watts. There's a whole bunch of stuff going on, and there's a storage ring, which gets you up to almost 6 kilowatts. Then there are two other storage areas, which get you up to near a kilowatt each, right? And actually make the beam go back and forth many times. And this was one of the big fights between Drever and Weiss. Weiss wanted to have a mirror where the stuff came in and went back and forth and back out through the same exit. Drever wanted to use a Fabry-Perot, which is a little harder to understand, but works better in reality. So, and then you will see there's output mode clear. There's a bunch of things that happen. So it's a lot more complicated. I had another movie. I don't know if we'll
In
see
an
it.
interferometer, a laser beam is split into two beams. Mirrors reflect the beams, so they meet again at a starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. A passing gravitational wave distorts space, making one arm slightly shorter and the other arm a little longer. The light waves do not cancel each other anymore, and we now measure a tiny signal in the detector.
So this is the easy part.
Now we add an extra mirror in both beams. In this configuration, the beams bounce hundreds of times back and forth between two mirrors, before returning to the beam splitter. The intensity of the light in these so-called Fabry-Perot cavities increases substantially. The cavities boost the interference effect a few hundred times. The sensitivity is further increased with two additional mirrors, which recycle the outgoing light into the cavities, and with a so-called mode cleaner, which removes disturbing noise from the laser beam. The light power in the cavities is increased to hundreds of kilowatts. Even more complex optics and electronics are required in order to keep the mirrors properly aligned and in position. Ground vibrations at most about 100 nanometers are nevertheless millions of times greater than the vibration caused by a gravitational wave. Therefore, all components are mounted on horizontal and vertical vibration attenuators, the best in the world.
They're actually triple pendulums for most of them.
While the ground is trembling, the mirrors and beams feel nothing of it, thanks to the super attenuators. Also, air presents a problem. It gives rise to unwanted vibrations, such as due to sound. Four so-called cryogenic traps provide an ultra-high vacuum quality. we can pick up hundreds of times more signal of a gravitational wave by extending the Fabry-Perot cavities to 3 kilometers. This and much more is needed to realize an interferometer for detection of gravitational waves.
Okay, so what's happening is you're using a lot of tricks. There's a lot of things that are going on. The mode cleaners, you'll notice laser usually has speckles, a lot of stuff. You don't want to have imperfections of the mirrors or the fact that the mirrors are vibrating. There's a lot of things you have to clean out and take care of. And so there's many things you do. And if you think about it, the 4 kilometers, or in the case of Virgo, 3 kilometers, if the beam is going back 300 times on average, because it's a statistical thing, that means the 4 kilometers is more like 1,000 kilometers that you're sampling over. And that's about as far as you can go because you're beginning to get into the frequency range in which you're trying to make the observations. So you're trying to make them as long as you possibly can because it's the strain, right, times the distance is how much it moves. Right? Okay? So then they get these you know, this piece of data in the first couple hours of being on. It was an engineering run, but the data are scientific data when they're not messing around, right? And you get this beautiful kind of a pattern. And so that's the thing that's sort of good. So here's another simulation. The black dots are the black holes. Underneath, color-coded, is the potential, the warp of space-time, and they're arrows that show which way the geodesics are. So you'll see space-time gets very distorted. There's a lot of things to see, so the movie slows down as they get close together, and you'll see the space-time gets more and more distorted. The waves are traveling out. And then what you'll see is the horizons in the black hole. Actually, there are 2 levels of horizons, an apparent horizon and an event horizon. And they actually separate slightly as the thing begins to merge. There's a lot, so it's slowing down now. They're not that affected until you get really close, right? And there you can see the apparent horizons touch, whereas the event horizons have not touched. Usually we don't care about that because we're doing static black holes, but this is not, right? And it rings down just like that. It's very fast how it corrects itself. That's all based on numerical general relativity. Oops. Okay, sorry. And so here are the waveforms observed and the templates, the waveform observed and templates, and the Hanford inverted and shifted by the 70 milliseconds so that you can compare one on top of the other. Okay, and so if you imagine you have 2 detectors and you have a time between them being 70 milliseconds, that means there is a circle in the sky that they could come from, but you also have evidence it's actually sort of quadrupolar. You actually can locate it to a hemisphere. So this is the probability from which that event would have come. So it's not very good. It's a lot of the sky. Telescopes, like the Hubble telescope, they can see like maybe one little spot here, something about that big, about how much they can see. So not so easy to try and follow this up, although big efforts were made to try and follow this up. And so the one place that did claim is the Fermi satellite, which looks for X-rays and hard X-rays and gamma rays, claimed to see a gamma ray burst at that time, and this is a color-coded probability of where it might have come from. Right? And you can compare, they agree. So at the time, we got all excited about this, because what were the chances? If there were really black holes, there shouldn't be anything from it unless they were charged or something else unusual was going on. So it could have told us some extra information. Well, that's, they were consistent. They were within 0.4 of a second, and there's only about 1 GRB per day. So we kind of got excited about it, but nobody else did. And so what's next? Okay, so there's a picture of LIGO at Hanford. It's getting ready to turn back on, and Livingston. And there's GEO 600 and Virgo, which will probably turn on in the springtime. It was supposed to be this winter, but it'll probably be springtime. And an agreement was just signed that there would be a LIGO in India, and that'll be probably after 2020. And there is a superconducting special one being done in Japan called Kagra, which will also probably be post 2020. So there will soon be 2 detectors running, and then 3, and then probably 4, and then a longer time period. So the time period, if you're a grad student, your postdoc time period, there will be additional systems in working. Okay, so we have a growing universe. The original LIGO is this section, well, let me blow it up. It's this section in red, that's the volume it was going. When LIGO turned on, it got out to this distance, and when it's finished, and with all the upgrades, if all the upgrades are possible, it should go out to that distance. So each one of those represents about a factor of 27 in volume, factor of 27 to 30, depending on what's going on. So it's not a surprise when it turned on, it went from no events in 5 years to probably 1 event per month, because you've got this huge fund. But if LIGO keeps being upgraded, it should get out to where there'll be an event every week kind of thing. But that's going to take some years, because one of the limitations, which I didn't have time to go over in this talk, limitations is the fact there's thermal vibrations. There's just thermal noise in the mirrors themselves. And they have to figure out how to cool the mirrors in order to get that down. So there's a lot of things, there's a lot of steps that have to be done. And there are people who are doing studies to do that. But right now, you're just trying to get a little bit beyond that yellow area in terms of what's going on. But you're in the business, right? Okay, so I got this cartoon, and the next 2 days after this, the event was in. So here are all the LIGO scientists, I don't know with the telescope, but the guy says he's hearing it, right? And of course the joke is there's a guy outside pounding on the wall. But it wasn't a joke.
1.4 billion years ago,
the other was
2
1.3
black
billion years
holes
ago.
performed a cosmic dance.
So some happened.
They spun around one another,
1.3,
coming
1.4
closer
billion years
and
ago, a lot of
closer
stuff was
together until finally they collided. This dance
Use some of
created
the same
ripples in the
video.
fabric of space and time, also known as gravitational waves. In December of 2015, those gravitational waves reached Earth and were detected by an instrument known as the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. Scientists with LIGO announced the detection of the 2 black holes on June 15th.
So there's the chirp again, but this is the second event. You'll see the frequency is different. It goes
This
up
is
higher.
only the second time that scientists have ever directly detected gravitational waves. The first detection, also made by LIGO, was announced earlier this year. Currently, all other telescopes and
is the
space
blurb.
observatories study the cosmos by collecting light or other particles. But the black holes detected by LIGO are not expected to radiate light. So by looking for gravitational waves, LIGO is illuminating otherwise invisible sectors of the universe.
This is for NSF's benefit.
For Space.com, I'm Calla Cofield.
Okay, so I looked at this, and I looked at the black waveforms in the Hanford and Livingston, and I said, these guys say these black holes have spin. I think I can see spin-orbit coupling, right? The angular momentum coupling between. It turns out there's other modulations going on there, but they do claim that at least one black hole has a spin of 0.2. 1 is the maximum spin you can have. So that in this event, the black holes had spin and had angular momentum from coupling. And you can see the effect in terms of going on. Turns out you have to look more carefully in the simulations to see it. But here, the black holes are a little different. This one's 14 solar masses, the other 7.5. The end product is almost a 21 solar mass black hole. And again, you get out a significant amount of power and gravity waves. Okay? So it turns out there was another candidate event in between. And so it's interesting. You look at this one, the biggest one with the biggest black holes has the shortest chirp, right? The one that has the middle-sized black holes has a bit longer, the candidate has a little bit longer chirp, and this last one, which has the lower mass black holes, has a much longer chirp. So if you imagine that there were neutron stars, this is going to go on a lot longer. This is what's going. You can tell the frequency, you can tell how long things last, right? Okay, and so here's the sort of little table that shows you the primary, the thing that's the bigger mass, 36, 23, 14, 29, 13, 7.5, end products, or out, three solar masses, 1.5 solar masses, 1 solar mass, and gravity waves. It's a huge amount of energy. Gravity waves, it's still tough to detect, right? And I have these sounds somewhere here. So you can hear, I think you can hear it. Maybe. Maybe not. This is the frequency shifted, so it's easier in the so it lasts longer, right? Because it lasts longer. You're detecting it longer, you hear it longer. It's pure note and then chirps at the end. Okay, so how do we know? I think that they made, this is a slide I got from LIGO. I think they made a mistake. It's gravity 15, 12, whatever it is. This is what the best fit template is, and this is the best fit for the first one. And here's what you would get if you had a binary neutron star. And you can tell the frequency is very different. Okay, so here's the timeline. They were in the engineering run, but now it's science run and engineering run. They made an observations. Just about a month later, they got the second candidate. Then there's a gap, and then just after Christmas, they got the third event. Right? So the rate is here approximating one per month, or one every 2 months on that sort of time scale. And then they shut off in order to do the upgrade, the partial upgrade. So LIGO is going to be turning back on. It should have somewhat better sensitivity. It should be getting at least the same rate on statistics of 3. Right? But 3 is not 0. Right? It's a big difference. Right? And so here's where they appear to be in the sky. The one from September, the one from December, and the one that was in October. And if you add the Virgo, the error, now you have three, you can either think of it as 3 circles or 3 things to co-locate. You get a lot better. That if Virgo had been on, you'd got an error circle that was actually small enough that you could actually start thinking about looking at it. Still not great for most big telescopes, but at least there was a chance that you have some stuff to do it. The other 2 need some other thing. It just has to do with configuration. But if you're getting these regularly, there are going to be some that you're going to get some reasonable time scale. And so here's some parameters. I'm running late, so I should go on further. There's other things I want to talk about. So there's initial LIGO range. Here's the bigger range that we're expecting to get, where you're adding huge more, big clusters of galaxies, so you're going to have many more samples. So there turns out there are 4 ways in which we're looking for gravity waves. The first one is ground-based interferometers, the first one to make the detection of ground-based interferometers that we know of. And you'll hear about space-based interferometers, LISA, laser interferometer space, LISA. There's pulsar timing arrays. That's one of the things that we pushed on, which is just like Hulse and Taylor's use the pulsar timing to let them measure their parameters. If you have a big array of pulsars out there and you measure the timing, you can look for space to move, the distance to move, and therefore the time delay to change. And you can look for a signal or for a stochastic background. And of course, we've been looking at the cosmic microwave background, and that's a plot that was, I think, from the early tentative report, and then maybe it's galactic dust, maybe it's something else, but so far the galactic dust safe planes are. But there are 3 that you can look for, and they're sensitive to different kinds of things. It may be that all 4 of these are going to be sensitive to quantum fluctuations and devices in the early universe, and then others for these kind of things like merging black holes and so forth. But one of the things, so this is just to give you the idea, the Big Bang produces stuff over a very long wavelength, the quantum fluctuations and phase transitions. There are supermassive black holes in the middle of every galaxy. When galaxies merge, eventually the black holes will merge. Those effects will be seen. And they're compact binary, both neutron stars and black holes that will do it. There are other things that can be producing gravity waves. So there's the possibility. This is just to show what you might do with fast, as an example of pulsar timing. So one of the things that was interesting that was immediately noticed, because people had not expected 30 solar mass black holes, if you have a pair of 30 solar mass black holes and you had LISA in orbit, you would see those 30 solar mass black holes for up to 10 years before they merged. And you could follow them as you orbit around the sun and measure the location and angle to much better than a degree, but also be able to predict the time at which they're going to merge to within a few seconds. You can tell people when to be on the air, when to watch for these things to happen, and where to be pointing your telescopes and so forth. So that's one of the reasons that ELISA is first being pushed to move forward, but also re-changing its configuration back to the LISA configuration. So there was a disagreement between NASA and ESA, and budget cutting in ESA and so forth. And then part of this capability was going away, and now trying to put the capability to be able to do this kind of stuff back into it. Now there are 2 Chinese sets of people who are proposing to do this kind of thing too. But it tells you what's going on. Whereas LISA originally was intended to look at these black holes in the center of galaxies really showing up in such a various way. And it should see a tremendous signal. It's like listening to a symphony. You try and decompose it into all the instruments. There's going to be, you have a confusion noise problem separating all the instruments, all the things that are going on. Okay? So then I wanted to talk about this briefly if Tony lets me have a little more time. Okay, so what are the astrophysical implications? So let's look at our survey of black holes. So the red ones are the new ones from gravity wave observations. And you will notice they are all sitting up here in the 20, here's the 20 solar mass blank. And here are the ones we have from X-ray binaries. There's a different population. Okay, well, I started worried about this problem a while ago. How did we get so when we had the first event, how do we get 30 solar mass black holes? Because our theory of supernova is you can't, right? There's a problem. In principle, you think you'll be able to do that. But it turns out if you try and make a supermassive star, like these first generation stars, one was called population 3, but they're the first generation stars, they tend to be heavy. You need for them to process and make the hydrogen and helium and the carbon, nitrogen, and oxygen up to silicon and iron so you can make stuff like the Earth. Right? If you don't have those materials, you can't make planetary systems as far as we understand. You certainly can't make rocky planets without them. You probably can't make hydrogens, probably can't make Jupiters and Saturns without some kind of rocky core. And so you need to have these supernova, you need to have these stars burn, make these elements, and you got to get this material back out and say it's supernova. When you do the calculations, you can't get it right. You can't get massive black holes. If you try and make things more than 20 solar masses, you can't get the star to explode. And if you try and take 100 to 150 solar mass star, the temperature in the center is so high you make electron positrons and you get these violent instabilities because you can transfer modes. It becomes very squishy and springy. And so you've got this problem, right? Generally, if you're above 40 solar masses, it's easier for the star just to go poof and become a black hole than to blow up. But we need that material. And I figured nature solved that problem, so I've been working with some colleagues to try and do this. We've been having trouble. Nobody's been able to get supernova above about 20 solar masses to explode reliably. We thought we had some additional mechanisms, the jets from these black holes, but that produces enough extra energy perhaps to do some of it, but it doesn't. It can't do. The 30 solar mass black holes are a problem. They're difficult to make. And so, where do these black holes come from? Well, up until we had this talk at the Journal Club, I thought, well, somehow we got to solve this problem because if the solar theorists are wrong, they got to be wrong. Somehow the universe solves this problem, right? But then it turns out there are other alternatives, right? And so one of this is that you make primordial black holes and you turn these primordial black holes into dark matter. Well, we looked up some papers at the Journal Club and there are limits, right? And this is the fraction of the mass of the dark energy that could be in primordial black holes, right? And you can see nowhere does it get up to 1. And we're trying to look up in this area here, which is the LIGO area, and you got to get down to below 10% of the black hole. Well, it turns out that's not impossible. You don't put it in a spike. You put it in as a low-level distribution. So there's 2 samples here, right? So 2 theories. You produce a primordial black hole through 2 versions of inflation. You could, in principle, do this with cosmic strings, but cosmic strings tend to go all the way up and run against this evaporation limit at the low. But if you have some clever way, Henry, to cut the mass off, you can do that. But here you get a mass cut off just because it's the horizon size, and it gives you a horizon size that's 40 to 50 solar masses. So you get an automatic cutoff, and then you distribute that around. So you can actually make this kind of a bump, and that kind of works. And so now the question is, can you make the black holes any other way, or do you gotta? Or we learned something about inflation. Does this fit with large scale structure, the cosmic microwave background, and the dark matter? And so this is an exciting area. I have to shrink it down a little bit so it fits, right? Because the scales aren't the same. But I have another plot that shows you the two models of inflation and the distributions you expect. And this is a log scale, so this is kind of a log normal distribution. And it's set basically by there is a cutoff in the horizon size, and then when you try and collapse it, you don't get everything in there, and so you get a sort of long. So you would predict the distribution. So if LIGO could get enough measurements, you could start distinguishing these kinds of distributions to see if the numbers are right. So, could be we're seeing a different kind of window in the universe than we ever thought we were going to see with gravity waves. Who knows? Okay. And then then I found this paper. Sorry, it's sort of blurry. I found this paper where this guy claimed Marco claims he rules stuff out. He added this curve in here. But I also found two other papers that claim he's 2 orders of magnitude off in this calculation, that instead of lowering it down to 0.01, he only lowers it down to 1. So, but it's not all fully published, so we can see. So stay tuned. This is a field that's really good. So we're getting tests of general relativity. So already with the first 2 events, we've got some tests of general relativity. Those are going to improve as we get more and more data. And so we got the first detection of gravitational waves. We've got the first observation of black hole binaries and the formation, the actual process of forming a black hole. We got the most luminous astronomical event. It's supposed to be, I'm sorry, I spelled it wrong. And we've got a new window in the universe and maybe a new window on physics. So it's a fun time. That's why I'm paying attention. That's why I'm giving this talk rather than one of the other talks I gave. So thank you.